Today, I'm presenting the paper Analysis and Attacks on the Reputation System of NIM. I'm Alexis, and this is a joint work with Professor Matt Green. To start with an overview of NIM, a regular passing NIM consists of a client connecting to an entry gateway, three middle mixed nodes, an exit gateway, and the destination. So NIM is a decentralized and incentivized mixed net. As of July 2026, there are 740 total nodes distributed across 62 countries. And what's exciting about NIM is that it has a cryptocurrency-based incentive system that rewards operators for running nodes. And NIM's reputation system includes two components, stake and measured network performance score for a node. And the reputation system is used to periodically select an active set of nodes that will route user traffic. So more onto the active sets in NIM. So they're selected every epoch, which is 60 minutes. And each node has an active set selection weight, which is a combination of stake ratio and performance score raised to the 20th power. And both are important components of NIM's reputation system. And notice here that for the 20th power, this really prioritizes performance score to encourage reliable node behavior. And the key observation here is that the selection formula is essentially a dimension reduction, which is combining two reputation dimensions into a single scalar score. And this shows that every monetary unit of stake is equal to a relatively small amount of performance loss. So to understand the composition of nodes in the active set, we did a 30-day data collection using NIM's Network Explorer. And we reported the stake and performance score for active set nodes every epoch. And as expected, only nodes with high performance scores are selected. However, within the active set, we can see a 70,000 US dollar stake per node on average, compared to just a $4 US minimum stake required to run a node. So this just shows that the high stake weight appears to be an implicit requirement to join the active set. So moving on to the attacks on NIM's reputation system. What the attacker would want is to gain control of the active set because it's only the nodes in the active set that will route user traffic. So a trivial attack here is just a baseline staking attack. Because we see the majority of nodes have near maximum performance scores, we can simply stake a large amount of NIM tokens on a set of adversarial nodes. But this is very costly, which is approximately 1.7 million US dollars to control just 20% of the active set. So what we want is to reduce the cost, which let us move on to focusing on the other metric of the reputation system, which is the performance score. They're measured by the centralized NIM network monitor that works at the following. It has a set of emulated NIM clients sending test packets down a loop path, which consists of one gateway acting as both entry and exit and three middle mixed nodes. So if the packet does not return to the network monitor, the question that arises is which node on the path should be blamed? And this moves on to the two metrics of blame attribution. The first one is the nature of information used to determine the responsible node, which we have either the current information or historical information as an assumption of whether the node is being honest or being adversarial. And the second one is the size of the set of nodes that can be narrowed down to when attributing blame. And NIM Network Monitor has two different measurement algorithms as at the time of the paper. That's a different combination of different blame attribution metrics. So this led us to think about performance score framing attacks. Because most nodes are at maximal performance scores, the obvious attack strategy is not to boost its own performance scores, but to reduce others. And a small performance score difference can compensate a substantial stake difference. So the overall attack strategy is that the adversary control two sets of nodes, a set of sacrifice nodes and a set of attacking nodes. So the sacrifice nodes are minimally staked, selectively drop packets to frame honest nodes and to boost the score of attacking nodes. And the attacking nodes are minimal to moderately staked, they're well performing, their goal is to replace honest nodes in the active set. So the attack outcome is that we want the adversarial controlled nodes to impart a disproportionately larger aggregate score reduction on the honest node than it receives itself, and is reminiscent of the creeping death attack first described by Singleton and Soverson in 2002. So now moving on to these two specific measurement algorithm that has been developed by NIM. So in the version 1, we have two testing phases. In the pre-testing phase, the network monitor selects a set of validated nodes from previously well-performing nodes. And in the testing phase, they use a set of validated nodes to construct test paths for the remainder of the network. And if the packet does not return, the sole blame is on the test node. So in terms of blame attribution, it is using the historical information to assume whether a node is being honest or being adversarial. And the blame attribution here in terms of the set size is just only one node. So the attack strategy here is also in two phases. In the pre-testing phase, the S nodes will relay all the packets in order to get selected into the validated set. And in the testing phase, the network monitor already viewed the sacrifice nodes as a validated node. And the S node will simply drop packets when the previous or next node isn't an attacking node. This attack is also self-reinforcing because after the testing phase, the sacrifice node isn't necessarily harming its own score, so it can be elevated into an attacking node as well. So moving on to the version 2 measurement, there's no pre-testing phase, and in the testing phase, all nodes on the test pass are the test node. And if a packet does not return, all nodes on the pass will share equal blame. So in terms of the metrics, this is using the current information in terms of blame attribution, and the set size is 4, which is very big. So the attack strategy is very simple. We just let the sacrifice node to selectively drop packets. So the overall goal of the attack in controlling the active set is to de-anonymize user traffic because only active sets nodes can route actual user packets. So there are two goals. The first one is gateway de-anonymization. It just mimics the services that operate similarly to NIM VPN's fast mode. And the second one is the full pass de-anonymization, which is similar to NIM VPN's anonymous mode. So moving from gateway to full pass de-anonymization, there can be two phases. The first phase is that the client will make new gateway reconnections. We estimate it to be the number of 50 that's realistic within a day. And then once the first phase that's achieved, we move on to the second phase. The client will send new packets because every new packet means a new mixed node pass. And the second phase can be achieved very quickly. To give an example, for 1,000 packets, that's equivalent to 20 seconds of transmission. So to simulate the attack, we want to understand the cost of baseline staking attack versus the framing attack. So to define the attack success, we evaluate continuous attack that occur across 24 epochs, and then we want at least one of the client's packets to route through an adversarial pass with 0.5 success probability. And the key result here is that for gateway de-anonymization, the staking attack costs approximately $250,000, while the framing attack only costs $2,800. And that is a 99% reduction in costs. And for the full pass de-anonymization, the staking attack costs $1.5 million, while the framing attack costs $4,200, which is also a 99% reduction in cost. We have also shown that even with some more ambitious attack success goals, we can also achieve a reduced cost around 90% using framing attacks, which is very effective. So moving on to the countermeasures of mitigating framing attacks. So there are two countermeasures proposed by NIM. The first one is alternative blame attribution. So this mirrors the version 2 design, which there's no pre-testing phase. And in this countermeasure, we assign the nodes to blame based on previous consecutive fail count threshold. However, this is still vulnerable to framing attacks because the attacker can simply drop packets before reaching the thresholds. And all nodes on the pass will receive equal blame, or only the honest nodes will receive the blame. And the second one is to separate non-active set and active set nodes testing. But we can still launch framing attacks with well-staked nodes once they're selected into the active set. And this shows a fundamental challenge in mitigating the framing attack, which is the inherent difficulty in accurately determining which node is responsible for a failed packet. So this lets me move on to the last point of countermeasures, which is monitoring the performance scores of nodes on the network to see if there's a sudden drop of performance scores in certain groups of nodes, while some other nodes are completely unaffected by this. So as you can see in the screenshots here, last month several node operators have been reporting that they're seeing their nodes having a lower performance score than usual, even though they're running their nodes properly as they did before, while some groups of nodes are completely unaffected by this. While we would expect an attack to have a signal like this, such pattern could arise due to other benign reasons as well, such as threat testing by NIM network. However, such monitoring the node's performance score is still a useful and helpful way to detect if there's anything unusual going on in the network. That's it. Thank you.